In chapter 5, we're going to be looking at eigenvalues and eigenvectors. They're really important in our study of linear algebra. In this section, there are 3 sections to this chapter. So this first one, we're going to be mainly focused on invariant subspaces, although we will introduce eigenvalues and eigenvectors. Maybe you've heard of them before if you've taken linear algebra 1 or matrix algebra, anything like that. So we're going to start with developing some tools or structures to understand operators, right? And if you remember, an operator was a linear map that maps to itself. So linear map that goes from V to V. And well, suppose T is an operator. So if we have a direct sum decomposition, such that V is a direct sum of all U1 to UM, where each Uj is a proper subspace of V, then to understand the behavior of T, we only need to understand really the behavior of each. That's called an invariant subspace. That's how, or sorry, I should say, this is what we call. This here is a little notation. It's Uj is invariant under T. But we need to understand the behavior of each Uj, so to speak. Right, so we just restrict it to a smaller domain where Uj is that subspace of V, and then we can kind of see how that works out. But to kind of help me explain this, I'll introduce a definition. So suppose T is an operator. A subspace U of V is called invariant under T if U in U implies that T of U is in U. Right, so it maps to the same kind of like an operator, just with a smaller domain, right? U's in U, so it maps to U. So let's take a look at some examples. Suppose T is an operator. We need to show that the following subspaces of V is invariant under T, right? So again, we're just going to pretty much apply the definition with these examples. So we need to show that these subspaces of V are invariant under T. So first of all, so this means that if 0 is in U, we should get that T of 0 is also in U. So on and so forth. So if U is in if U is an element of 0, the 0 vector, then U is 0, and therefore T of U is 0, which we know is an element of the set 0. Well, therefore, the 0 vector is invariant under T. So if you want to go ahead and pause, you can try the other ones. This next one is pretty straightforward, right? If we have a vector in V, we're mapping it to V, so it should be invariant under T. So if using vector space V, and remember, T here is an operator. So T of U must be in V as well. Therefore, V is invariant under T. Next, the null space. So if U is in the null space of T, then T of U is equal to 0, right? By definition of null space. And therefore, T of U is in the null space of T. Again, because of the fact that we're dealing with operators, we're dealing with the same vector space. Therefore, we can conclude that null T is invariant under T. Last one, if used in the range of T, well then the map is also in the range of T. Right, again, don't overthink this. These examples are pretty straightforward, nothing too complicated. But we get that range of T is invariant under T. And there's another example, but before we even move on, I know a question I've been asked before is, does T have to be an operator, or can we have a T be an operator that has invariant subspaces that aren't 0 and V? And the answer is yes, and we're going to actually see that later. And or here we have that the null and the range are invariants, right, under T. But although those are invariant under T, they don't necessarily provide easy answers to the question about existence of invariant subspaces, other than like 0 and V. Because the null space of T may just always equal 0, and the range of T may just always equal the whole space V. So we'll get to that. But last example, suppose that T is an operator that maps from the vector space of all polynomials with real valued coefficients. And we define that operator by mapping a polynomial P and then just taking its derivative. So is this invariant under T? Well, let's see. So in this case, P sub 4 of R, so the polynomials, the vector space of polynomials with degree at most 4, which is a subspace of the set of all polynomials, is invariant under T because, why? Well, because if P is a polynomial that has at most degree 4, well then its derivative also has at most 4, right? And in this case, the derivative will have degree 3, but it's still an element of this space because it's just at most 4, right? Not exactly 4, at most 4. So it still remains a polynomial in that vector space. Therefore, it is invariant under T. So that's pretty much an introduction about invariant subspaces. We're going to obviously be looking more into it later. Just an interesting fact that the most famous unsolved problem in functional analysis, you probably haven't taken functional analysis. That's for sure a graduate course. But the most famous unsolved problem in functional analysis is called the invariant subspace problem. And it deals with invariant subspaces of operators on infinite dimensional vector spaces. So here we're dealing with finite dimensional. So now we can introduce, so this is a little kind of motivation for what we're going to be going over next. So take any vector v in the vector space v, where it's not 0, and let u equal the set of all scalar multiples of v. Right, so the set of u is just v scaled by any lambda, which obviously is in the span of v, right? By definition, just any scalar of v. If u is invariant under an operator t, well then tv is also in u, right? Because it's invariant under the operator t, and hence there's a scalar lambda such that tv is equal, oh, it's right here. tv is equal to lambda v. Right, and again, why? Well, because this is in u. This is in u, so we can find a lambda such that that equation is true. Also, I should mention, before I do move on, this equation here, well, it does have just v, we're scaling v, right? So it's a, so span of v is one dimensional. Right, it's just one vector and we're just scaling that vector. And in fact, this is pretty, I guess important. Yeah, important is the right word. Uh, so much so that we do give this a name, and this is what I was mentioning before. So suppose T is an operator and a number lambda is in F. This is called an eigenvalue of T if there exists a vector V in V, such that if the vector is in 0 and TV is equal to lambda V. So again, it's an eigenvalue if there exists that vector such that lambda times that vector is equal to TV. Right, and that, again, that's coming from over here. So we have this theorem. Suppose V is finite dimensional and T is an operator. Lambda is a scalar in F. Then the following are equivalent. Lambda is an eigenvalue of T. T minus lambda I, remember the identity, just takes x and maps it to x. So lambda I, T minus lambda I is not injective, T minus lambda I is not surjective, and it is not invertible. Those are all equivalent. And the proof is actually easier and shorter than you might expect. That's all it is. Look at that little box. So conditions A and B are equivalent. Now why? Well, just tamper with this equation here. Right? It's just equivalent to this equation. Just bring T equal to lambda V. And then we got it. Right, so that's why they're equivalent. Um, also, here lambda, uh, actually, no, I shouldn't say that. I was thinking it's just going to confuse you. Instead, just recall, remember when we were first talking about operators? I believe in chapter 3, we were talking about operators, and we were mentioning how a theorem, or we got a theorem where injectivity, if we have injectivity, we get surjectivity as well, and therefore inverses or invertibility, right? If we had either of these three, 1, 2, 3, then we would get the other two for free. And that's when we're dealing with operators. Well, in this case, we are also dealing with operators. Therefore, B, C, and D are equivalent from that previous theorem. If you need to go back, you can go back. I believe it's in the section of duality where we went over operators for the first time. And now we can bring up examples, right? Examples are always useful. So, suppose T is an operator, and it's defined by this linear map. You can verify that that's a linear map. We need to find the eigenvalues and eigenvectors. I'm seeing here that I haven't defined eigenvectors. I may have forgotten that one. So before I even do move on, let me just define eigenvectors. I might even have it later on, but in case I don't, let me define eigenvectors. And you can copy this down or just make sure you have it. So we suppose T is a operator and lambda is in F. Uh, so lambda here is an eigenvalue of t. A vector v is called an eigenvector of t corresponding to lambda if v isn't 0 and tv is equal to lambda v. So in this case, an eigenvector, all it is if we have this equation here, right, where t is an operator and lambda is an f, where lambda is an eigenvalue, well then v is an eigenvector. So this is the eigenvalue, these are the eigenvectors. Eigenvector. And lambda is an eigenvalue. So that's what an eigenvector is. So if you need, go ahead and pause. I'm going to erase this because we're going to go over the example. Okay. So first of all, before I even do go on, you might be wondering, will it really make a difference that we're dealing with real numbers as opposed to complex numbers, and vice versa? Well, in this case, yes, and we'll see. So if f is the real numbers, then t, this transformation here is a counterclockwise rotation by 90 degrees about the origin. Now already you should be thinking something. If we have a vector, here you go, there's a picture. This isn't the picture for this exactly. This is, as you can see, that's not necessarily 90 degrees, although it's a good picture because it is rotating counterclockwise. But as you can see here, v, that v there, if we multiply by lambda, what's that going to do? It's either going to go this way or this way. So if we're rotating it, we can already tell that what? This blue line that's going to end up somewhere here, is that going to be a scalar multiple of our vector v? No, right? So let's just go over how we can do this, how we can go about doing this. So an operator has an eigenvalue if and only if there exists a non-zero vector in its domain that gets sent by the operator to a scalar multiple of itself. Right? And as the picture just showed you, that is not possible in this case. So therefore, t has no eigenvalues. Now, will there be eigenvalues for complex? Well, to find eigenvalues of t, we must find the scalars, right, lambda, such that this is true, right? This is the equation we're looking for. Again, this is an eigenvalue, and these would be the eigenvectors. And we need for this to have a solution other than w equals z, which they both equal 0. And why is that? Well, by definition of eigenvalue, right? V can't be equal to 0. That can't happen. That is not interesting in any case, so that's why we're excluding that 0. So the equation above is the same thing as saying negative z is equal to lambda times w, and w is equal to lambda times z. Now, why is that the case? Well, t is wz, which is equal to lambda wz, right? And what does our transformation from over here do? it maps it to negative z w. So that's why we need a lambda wz which is just negative z and lambda z equal to w. And that's how we get these two equations. So I'm going to erase this. Well, if we substitute the value for w, right, we're just going to plug this w in to this one here. To the second equation, we get this equation now. Negative z is equal to lambda squared times z. Well, now we can divide by z since we know it's not equal to 0. And we get that negative 1 is equal to lambda squared. Now, what is lambda going to be in this case? Well, lambda is going to be equal to I and negative I. Right? So those are our eigenvalues. And the eigenvectors corresponding to the eigenvalue I is a vector of the form w and negative wi, where w is a complex number. And the eigenvector corresponding to the eigenvalue negative I is a vector of the form wi. So that's how we get our eigenvalues and our eigenvectors. And you can easily verify, right? You can take I, for example. Go to I. Set that equation up, and you'll verify that indeed they are eigenvalues and eigenvectors. That's how you can do it with each eigenvalue and its corresponding eigenvector. So now we can move on to some theorems of eigenvectors. Let T be an operator. Suppose lambda 1 to lambda m are distinct eigenvalues. And v1 to vm are corresponding eigenvectors of those eigenvalues. Well, then we claim that all the eigenvectors are linearly independent. So the way we're going to do this is by contradiction. So let's go ahead and prove this. Suppose they're linearly dependent. Well, we're going to let k be the smallest positive integer such that vk is in the span of all the previous vectors. Right? And we know this is possible because they're linearly dependent. And because of that, we know that the linear dependence lemma, we can get a vector that's in the span of the others. So that's how we're doing this. So there exists scalars a1 to a sub k minus 1, such that vk is a linear combination of all those vectors, of all the previous vectors. Again, because it's in the span of those vectors. Well, if we apply t to both sides, we're simply going to get that lambda k times vk is equal to this now linear combination where all the lambdas are inside our linear combination now. They're being multiplied. So if we multiply both sides of the first equation, meaning this one here, by lambda k, and then do what? Subtract this equation, we will get exactly this. So 0, because this over here is lambda k, vk, and we're subtracting exactly the same thing over here. So that's why we get a 0. And then we get here, we get lambda k minus lambda 1, because here we'd have a lambda k. And then over here we have lambda 1, so that's why it's a lambda k minus lambda 1. Same thing with the other lambdas, lambda k all the way to lambda k minus 1. And we get that 0 is this equal to this linear combination. And now remember, we chose k to be the smallest positive integer, satisfying that it would be in the span of that list, right? So we know that this list is linearly independent, right? If that's not clear, take a second to think about that. I'll explain it, try to explain it a different way. So if vk, so we know these are linearly independent. Why is that? Well, because we chose vk to be the first vector that's in the span of the previous vectors, meaning the first vector that makes this list linearly dependent. That's how we chose k. So that's how we know that the ones before that are linearly independent. Well, then the equation above, right, this last equation here, implies, because they are linearly independent, and by definition, that implies that all a's are equal to 0. Well, then that would mean that vk is equal to 0, right? From our first equation up here. Well, if the right side is equal to 0, well, then the left-hand side is equal to 0, so vk is equal to 0. That contradicts our hypothesis that vk is an eigenvector, right? Because eigenvector by definition can't be equal to 0, and therefore our assumption that v1 to vm was linearly dependent is false. So one last theorem. This one, it's a bit clever in its proof, but it shouldn't be too hard to understand. So suppose v is finite dimensional, then each operator on v has at most dimension v distinct eigenvalues. So let t be an operator. Suppose that lambda 1 to lambda m are distinct eigenvalues of t. We're going to let v1 to vm be corresponding eigenvectors. Well, then the previous theorem, right, the one we just saw above, we know that v1 to vm is linearly independent. Right? So what does that mean? That just means that the m, the number of eigenvectors, is less than or equal to the dimension of v. And that ends the proof. We're almost done with this section. Now we're going to be looking at restriction and quotient operators. So what is that? So first of all, definition. Suppose T is an operator and use a subspace of V invariant under T. Then the restriction operator, where U is invariant under T, is defined by mapping U to TU. Right, so in this case, we're restricting the domain and mapping it to TU. We have the quotient operator. So if you have the quotient space T over U or T slash U, that is also an operator. Oh, sorry, I didn't mean space. Here, this is a linear map, right? A quotient map, I should say. If you remember quotient maps, we had previously defined it with pi. Pi, not the rational number, just a variable. Irrational number, I should say, not the variable. So we have the quotient map here, which is an operator. Again, we're restricting the space now. The quotient space is V over U, which is defined like this. And again, if you remember affine subsets and how we define quotient spaces, this definition, well, should make sense. So the quotient map maps v plus u to tv plus u for every v in our vector space V. Something I should note is we should probably verify that the quotient operator even makes sense, right? Because what if this definition isn't even well defined? So to verify that, if v plus u is equal to w plus u, well then we know that by a previous theorem, we previously went over this not too long ago. But there's a theorem that told us that this is equivalent to what? Oh, here, to v minus w is in u. So if v plus u is equal to w plus u, well then v minus w is in u. And again, we need to verify that v plus u is equal to w plus u implies that this is true. So again, we're going with the theorem. This here, we got this. There's an equivalence between those. And again, we had gone through a theorem about that. I really can't remember what section. But because u is invariant under t, well then t of v minus w is in u, right? Just by definition of invariant. Which then implies that tv minus tw is in u, and we're done. So for both of these operators, it's worthwhile to pay attention to their domains. And if you have to spend a moment thinking about why they're well defined, I already showed why one was well defined. But we can look over a few examples now. So first of all, this is our problem, 3 parts. So define T as an operator, obviously from F2 to F2, by, this is how we're defining that operator. And let U be x0 for all x and f. We're going to show that U is invariant under T, and that U invariant under T is the 0 operator on U. So let's go over that one first. So again, that's just how we're defining the elements of U. For x comma 0 in U, we have, by our linear map, that tx0 is equal to 0 comma 0. Right? Why is that the case? Well, because this is y. Y is equal to 0. And our linear map over here, or sorry, our operator is telling us that we map to y0. So y is 0, and then we have 0, so that's why it's 0, 0. And 0, 0 is in U, right? Because we can just let x equal 0, and now it's in U. Therefore, U is invariant under T, and U invariant under T is the 0 operator on U. Next thing, before we even go on, there does not exist a subspace W of F2 that's invariant under T, such that we can have that the direct sum of U plus W is equal to F2. So why is this the case? Well, suppose W is a subspace of V, such that it is the case that the direct sum is equal to F2. Well, we know the dimension of F2 is 2, right? And a dimension of U, we know, is 1, right? It's just X. So the dimension of W should be 1. Well, if W were invariant under T, then each non-zero vector in W would be an eigenvector of T. However, where do we run into a problem? Well, we can see that 0 is the only eigenvalue of T. Therefore, V cannot be invariant under T. Therefore W can't be invariant under T. Is that what I said? I don't even know. Last one though. The quotient map, which is an operator, is the zero operator on F2, this quotient space, F2 over U. Well, for xy in F2, we have that the quotient map takes xy plus u to t of xy plus u, right? That's by definition of quotient operator. That we know is equal to y0 plus u, again, just because of how it's defined up here. And we know that is equal to 0 plus u because of how u is defined. So this last equality, this holds because, just so you can have it as a reminder, not just me saying it, because, well, y0 is in u. Right, so this shows that this quotient mapping is indeed the zero operator.